So we were talking about algorithms when last we met. Now we're going to dive into what they really mean for us. There are a couple algorithms that you do need to know for the AP computer science exam. Not necessarily how to code them. Knowing an algorithm does not translate directly to code. The algorithm is the process for doing something. For example, an algorithm for making a peanut butter and jelly sandwich would be put the bread down on the counter, spread peanut butter on both sides, put the jelly on both sides, close it, cut it into 4 corners, cut the crust off, stick it in the box. That's an algorithm for making a peanut butter and jelly sandwich. You might find you have a better algorithm, which I highly doubt. But you might think. So what is an algorithm? It's a pattern that accomplishes a task. That's it. Very straightforward. Some type of pattern. You guys have probably all done algorithms in the past. You may not have written down an algorithm. You may not have analyzed the algorithms that you follow, but there are algorithms in every moment of your life. Algorithms have to have a clear order, and the instructions have to be clear. The language has to be clear as what you're doing. You can't have generalizations in algorithms. They have to be very process-oriented. They must have operations that can be done by a computer. If you're talking about a computer algorithm. Clearly, making a peanut butter and jelly sandwich is not something that's easily accomplished by a computer. But for computer programming, all the operations that are in the algorithm have to be accomplished by the computer. They have to produce a result, and they have to stop in a finite amount of time. The algorithm has to have an end. You could then go back and repeat the algorithm, but the algorithm absolutely has to have some type of end goal. So, what makes a good algorithm? Take a look at these categories and see which one of these are the most important in this list. Pause the video and we'll come back. So, if we look at these, it's fairly easy to make an argument for the importance of every single one of these. However, there are circumstances where some of these are more important than others. And it changes depending upon the algorithm, depending upon what you're trying to accomplish. Sometimes security is the most important part. That might be the most important part of your algorithm is security. If you're working in the stock market and you're trying to prevent people from figuring out what your algorithm does, you may not care how easy it is to code. You might be more concerned with the security of it. If you have an algorithm that is public to the world and you're just trying to make something very efficient and very cleanly done, like, I don't know, baking a peanut butter and jelly sandwich, nothing secret about that, then you might want something that's fast and easy to code. So these kind of take on different levels of priority depending upon what your algorithm does and what you want to use it for. So this is actually a set of questions that you have to ask every time. This is not which one is important universally. This one is which one is important now? What do I want to focus on when I'm making this algorithm? And then the last question there, nobody kind of mentioned, how do you measure these? How do we measure reliability of an algorithm? How do we measure the security of an algorithm? Got to have somebody come in and hack it? Possibly. People do that. How do we determine if it's easy to maintain? What's the criteria for that? What makes it easy to maintain? Is it well commented? Is it something that's easily accessible? Is it something that has to be decompiled? Do you have to hire somebody in another country to come in and work on it? Which is a realistic possibility. If you have a business where your coders live somewhere else, you might have to say, well, if we have to do updates, we're going to have to do this at 3 o'clock in the morning because that's where they get their productive time done. And we're kind of relying on them. So we have to have the ability to have staff in at 3 o'clock in the morning to get this updated. Which, by the way, works as a good balance because most American businesses, when they're shut down, the businesses on the other side of the world that are providing the code and doing all those updates are open. So you don't want your computers being updated while your employees are working on it. So it actually works out well in terms of that balance. So that may be a good thing in terms of easy to maintain. You're getting out of your own way. So the levels of importance depends upon the task. Why do we have to analyze these algorithms? Well, we want to know how these are going to perform. We don't want to just design an algorithm, kind of throw it out there, and hope it does well. Hope it kind of does what we want. We want a little bit better information before we deploy all the resources to make this algorithm a reality. We need to make some decisions as to, is this the best algorithm for the circumstance? We actually had a situation like this with Tweet Tester. You guys had an algorithm. You created an algorithm. I didn't call it an algorithm, but you created an algorithm to go through a tweet. Then I showed you my algorithm. You may make an argument that yours is better than mine. It's possible. But I could make an argument that I think mine's probably better than all of yours for several reasons. So that's some type of thing you'd have to be able to do to defend your algorithm. Why is yours the best? Why should they go with your algorithm over anybody else's? So we're going to look at a really kind of cool algorithm here. There we go. So this is a set of prime numbers. I'm going to try to pronounce this right. It's the sieve of Eratosthenes. And the goal is to take a set of prime numbers and sort through it in a quick way, or a set of numbers, excuse me, and sort through it to find all of the possible prime numbers. So what I want you to do is pause the video, take a look at this, see if you can just look at it and come up with all the prime numbers right off the top of your head. So if you take the hint here and you start with 2 and cross off all the multiples of 2, we get that. Then we follow the same algorithm and move up a number. 3 is a prime number. So we got to first ask ourselves, is the next number a prime number? Yes, it is. Let's cross off all the other multiples of 3, because anything that's a multiple of 3 can't be a prime number. Then 5. Then 7. Everything else is prime. That's pretty freaking cool how fast that worked. Because you can see that you have eliminated every other number except for the prime numbers. And you could go through the list. As you would follow the algorithm, you say 11. Any multiples of 11? Nope. 13? Nope. 17? Nope. 19? Nope. And so forth. 23, 29, 31, 41, 37, 47, 43. Gives you all the prime numbers in a very, very efficient method. Now that you see the algorithm, it might make sense to you that that truly is the best way to do it. But until you thought about it, a lot of you went through this number by number. What numbers divided evenly? What numbers divided evenly? Can I divide? And just going through number by number and analyzing number by number by number. Wouldn't this have been so useful in like 6th grade? That would have been fantastic in 6th grade. This has been around for a really long time. Really, really long time. Wish I taught this to you in 6th grade. So all of our primes are highlighted in blue. So let's talk about this in terms of code. Now, this is where it gets a little complicated. Translating an algorithm to code requires you to go through and come up with an iterative process. So let's jump back for a second. What is the repeatable process we found? And how do we know we're done? Those are the 2 questions we need to answer in order to code this. So in this algorithm, we really need 2 loops. We're going to progress through the prime numbers, one at a time. And once we found a number, let's say we start with 2, we're going to go through the entire list and replace everything that's a power of the 2 with, let's say, a 0. Then we move on to the next value, and then replace everything in the list that is a power 3 with a 0. Then we move on to the next value. Well, 4 is not there. 4 is a 0. So the next value will be a 5. So essentially, we're going through and getting to the next value that's not a 0. So find every value in the list after 5 and mod that by 5, replace it with a 0. 8's a 0. 7's not a 0. So as we go through this, we start filling up the list with zeros, or whatever value you want to put in there. In addition, as we're going through this on the outside loop, we're just going number by number, skipping over anything that's a 0. So the inside loop is fixed. Every time we do it, we have to go through all 50 values. Well, maybe not all 50. Maybe we can start where our index is. Like, we don't have to go back to the beginning. We already eliminated those. So maybe we could start here, but then it's still a fixed number of values. Starting here, going all the way to 50. Starting at 11, going all the way to 50. Starting at 13, going all the way to 50. So every time we have a fixed number of times we go through the loop on the inside. That's a for loop. On the outside, we're going to have a while loop. While what? What's the condition we're testing? We look at this last value here, and we went through the entire list trying to mod everything by 47. If nothing was divisible by 47, we must have found all the primes. So there we get that idea of a flag. We set the flag that all the primes have been found, or no primes have been flipped over, and that's what stops our loop, our while loop. That's the end. So now we've talked about this, you would go ahead and then write this out in words. When you're brainstorming code, you go ahead and you write this whole process down in words. Start trying to refine it, going through looking at the individual pieces. Before we start coding, this is one of the mistakes you guys made with Tweet Tester. You started coding right away. There should have been a lot of words and a lot of thought and a lot of conversation before you ever started coding it, rather than jumping right onto those keyboards. So now we can start looking at the code. So we're going to make a flag, and we're going to clear out just true and false. See, rather than making the list a list of numbers, don't we already have a list of numbers by just the indexing of the array? The array itself is indexed with a list of numbers. So if I make an array of size 50, it's going to be indexed 0 through 49. I just have to increment that up by 1 when I'm checking it. And I could just check to see if it's true or false. Is it prime or not? So we start with everything as false. So we're going to go through, and well, actually, I think in this case I set everything to true. So we set everything to true and say everything is prime. So we're going to assume all the numbers are prime until it's not, because we haven't checked them yet. So that's our first step in this process. Make every number assumed to be prime. Here we're also going to set up an output. So we have a nice little loop here at the very end that runs through. We can start at number 2 because we don't have to start at 1 or 0. And we're going to run through our list all the way up to the length, and we're going to print prime, and we're going to print it out that it is I plus space. That way we're printing all the prime numbers in the list. So this last bit here, if it's true, we print I. So if it's still true after we're all done, we're going to print I. Now for the meat. I got this with 2 for loops rather than a while loop, because the way we structured this, the true and false is set up inside of this. But we could have done it with a while loop as well. So on the outside loop, we go from 2 to D++ to the length of the prime list. And then on the inside loop, we're going through every single value every single time. And we're starting at where the last one left off. So int I equals d. So in the first case, we're starting at 2. And here's our test. If I mod d, you guys were right, we're going to use a mod. If it equals 0, we're going to say it's not prime. That's it. Just set it so it's not prime anymore. Make it false. So we could have done this by replacing with zeros or putting in a null. That could have worked as well. Anybody see a problem with this code? Pause the video, take a look at it. So if you look through this issue, what happens is that at some point, d and I will be the same value. It'll happen essentially for every prime number. It happens at 2. It happens at 3. It happens at 5. When the two numbers are equal, 2 mod 2 is 0. And it's going to say, oh, wait, that's not a prime number. So we got to fix that. That's not going to work. The idea is right, except for those individual prime number cases. We got to jump in and fix that. So when d is 2 and I is 2, we mistakenly end up saying 2 is not prime when it is. So what we do is we just take d and fix it so we are one more, d plus 1. I starts at 1 after the value that we're on. And that is actually it. That's the sieve algorithm right there. Just this little piece. 2 for loops running through and do that will allow you to find all of the prime numbers in any list. You could set this array up to be size of 1 billion. And this program will go through and print out all the prime numbers for 1 billion, from 1 to 1 billion. That's pretty cool. In fact, it becomes really important in the process of RSA encryption. There's a lot of stuff in the news nowadays about hacking people's accounts and emails and all that. And how do they do that? Well, one of the ways that they theoretically can do it is if the RSA encryption is not secure enough, it's not a high enough level, you can go through and brute force, try prime numbers, to figure out what the security key is. You see how easy it is to generate prime numbers. However, they use 100-digit prime numbers for the lowest level of RSA security. That's going to take a very long time, even running through this loop, to break, even at the speed of a computer. So it becomes much more difficult. That's why things like high-level securities at corporations and things, they do very cool things. Like my brother, when he used to work for a corporation, he would have a key fob that he would take home. And the key fob would update the password randomly. Your dad has that? And he had to use that password in order to get through the system. And it had a partner in the computer system. So the two were not linked. They just worked on the same algorithm. So there was no connection between the two. You could effectively say they were air-gapped. There was no Wi-Fi, and they're not running Wi-Fi. They just happen to be running the same algorithm to come up with these sets of numbers. And they're always in sync. So if you have that key fob, you have your password, and it's randomly generated. We talked about the idea of randomness not really truly being random, which is critically important in that case, because if it truly was random, you wouldn't be able to accomplish this. Two computers running the exact pseudo-random calculations can come up with the same list of numbers. So the little key fob is little computers going through and calculating all these random numbers. And the computer on the other end is calculating all the random numbers, and at any given time, the passwords always match. So as long as you don't lose the key fob, you're set. You can log in. That's a pretty cool security system because every time the password changes. Now, that would be a pain in the neck for most of us to have to go ahead and do that. But for high levels of security, when they're remotely logging in, that's actually really critically important. Again, going back to the idea of what's important. In that case, security would be highly important. So That is about it for algorithms. I'm not really going to have you code many algorithms because we've been coding algorithms all along. So there's really no practice assignment for this because we're going to continue practicing this throughout the rest of the year. Essentially, this is our main focus. It's writing algorithms. What we want those algorithms to do will become more apparent. For the AP Computer Science test, the algorithms that you're going to have to know is search algorithms. You're going to have to know sorting algorithms. You're going to have to know how those algorithms work. Not necessarily how to code them, but you do have to know how they work. For example, for the sieve, we kind of needed to know that we needed two loops. We could argue whether it's a while loop or a for loop, but we needed to know we needed two loops. That's the understanding of the algorithm you would have to have at that level. Not just how it works and how to do it on paper, but have a general idea of the pseudocode required or the paragraph that you would write out before you go ahead and actually code it. That's how you have to know these algorithms. So I want you to work on the exit ticket. In addition, I have assigned the labs. So you guys can be working on the pictures lab. If you have questions still about the Magpie lab, you probably should have come see me by that already. But if not, you should be finishing that up as well. That should be done. Really should be done. And you should start working on the pictures lab. The first 4 activities are what you should be working on for the pictures. And you should be able to handle all those. Most of it's running it and taking a look at it and messing with the different controls that are in it. Okay? And that's it for today's lesson.